Start recording. Voila. Okay, so work 9 worksheet this week, section 6.2. There's 7 questions, but a lot of them are just like low lobs, underhand, so you can just knock them right out of the park really, really quickly. Some of them are not so straightforward, but yeah, maybe we can hit some of them out of the park really quick. So let me see if I can identify the ones that we should be able to answer really, really quickly. And then I'll give you, a couple of minutes to see if you can knock them out of the park really, really quick. One surprisingly does take a little bit of work. I guess it's not, okay, no, it's not as easy as some others. So 3, okay, let's call these quick questions. Okay, so quick questions. QQs. Okay, so question 3 should be quick. Okay, so question 3 is prove that phi n is even for all n greater than or equal to 3. Okay, that one might not look quick, but it is. And kind of as a hint, let's think about this first before I kind of let us go and try and work it out. If we want to prove something about phi n, do we remember what I said on Tuesday? What's our like automatic thing that we should try, right? So if we ever want to prove something about the Euler-Toscan function, what are we trying to prove something about from a group theoretic viewpoint? Anyone remember? No? Okay, so the hint, remember, is that the order of un is phi n, right? So if you want to prove something about phi n, it's often enough to prove something about the group of units for Zn, right? That group un that we've played around with so many times. So if you can prove something about that, you can probably prove something about un. So think about what it means for something to be even, and then translate that into a statement about, and remember what we're doing this week, right? It's Lagrange's theorem. Translate that into a statement about un and see if you can prove it. And there is a natural thing to do it there. Question 4 is a one-liner. Okay, so if the order of G is 21, every proper subgroup is cyclic. This is a one-line proof. It might take a second to think about it, but give it a shot. 5 needs a little bit of work. 6 needs a little bit of work. 7, you know what? Maybe I'm going to promote 2. I think 2 is kind of a one-liner as well. So maybe I'm going to put 2 as one of our quick questions. So you know that H and K are subgroups of G. And the order of H is equal to, 12? And the order of K is equal to 35. Find the order of H intersect K. Okay, so each of these questions are about 1 or 2 lines. They're not designed to be terribly long or arduous or anything like that. So what I'm going to do is let's spend 5 minutes, see if we can think about how we would do them. Just do your best. I say that they're quick and easy, but if you don't kind of see what to do, they're not obvious. So don't feel bad if you don't get them. But let's spend 5 minutes, see if we can manage to crack down what it is that we're supposed to do. And then I'll take them up in about 5. Okay, so let's start with this. Questions 2, questions 3, and question 4. All right, 5 minutes. Okay, so we're at 5 minutes. Let's see. These are the quick questions, like I said. So let's see if we can knock them out of the park really, really quickly. I'm just going to write underneath them. Oh, man, where did this 3 go? Oh, it goes there. All right, so the solution to this one comes from recognizing H intersect K is a subgroup, right? So H intersect K must be a subgroup of H, and it's also a subgroup of K. right? So by Lagrange's theorem, I'm just going to call that LT because I don't want to write it out. We're going to use it a lot, right? So by Lagrange's theorem, we must know that the order of H intersect K must divide the order of H, right? Which we said is 12. And also H intersect K must divide the order of K, which is 35. So whatever H intersect K is, it has to divide both 12 and 35, but the only number which divides both 12 and 35 is 1. All right, so but the only number which divides both 12 and 35 is 1. So that says that this has to be the trivial group, right? It's just the singleton, which is the group identity. So that's what I mean by that's a fairly quick one. You're just like, oh, by Lagrange's theorem, this has to divide both 12 and 35. So boom, we're done. Okay. For 2, oops. Wow, that was a weird thing. Cyclic. Okay. So the proof for number 3, does anyone have an idea? So I said we need to prove something about U of n. So we want to show that 2 divides phi n, right? That's what it means to be even. 2 must divide it. And so it's sufficient to show that there's an element of order 2 in UN. So by LT, by Lagrange's theorem, it suffices to show there is an element of UN of order 2. Okay, can anyone think of an element of UN that has order 2? Any ideas? No one? No one's got any idea? Okay, well, there is a natural element, and that element is -1, right? And if you don't like -1, you're like, hold on a second, you're not allowed to choose -1. Well, it's modular arithmetic, so that's the corresponding, that's n-1, right? So indeed, the equivalence class of -1, which is the equivalence class of n-1, has order 2, right? And you can see that however you want. -1 squared is certainly 1, right? -1 squared is certainly the equivalence class of 1. Or if you want to do it from this standpoint, this gives you the equivalence class of n squared minus 2n plus 1. But remember, this is mod n, right? So anything that has an n in it dies. So that gives you 1. So yeah, UN has an element of order 2 by Lagrange's theorem. The order of the element must divide the order of the group. So boom, we've shown that phi n is even. All right, thus phi of n is even. Voila, okay? So, you know, I said they were short proofs. I mean, I'm doing a fair amount of writing, which is making them seem maybe a little bit bigger, but the idea is relatively straightforward. And if G is, the order of G is 21, every proper subgroup is cyclic. Does anyone have an idea for how you can just like immediately be like, yes, this is clearly true with almost without writing anything down? Exactly. All of its factors are prime. Perfect. It's a solution. I mean, technically one of its divisors is 21, but only if its only proper divisors are prime, right? But exactly, I know what you meant, right? So the proper divisors are technically, I guess 1 is in here too, but it's 1, 3, and 7, and any group of these sizes is cyclic. any group. So even though one isn't prime, trivially, the trivial subgroup is obviously cyclic. And any group of these sizes is cyclic, right? So we're done. Okay, so that's it. So that takes care of 2, 3, and 4. Those are some pretty quick ones. Now, I think this is kind of a nice place to pivot into 5. Okay, so having just done 4, let's pivot into 5. And so question 5 asks, true or false, if every proper subgroup of a group G is cyclic, then G is cyclic, right? So true or false, if every subgroup, let's say proper subgroup, group of G is cyclic, then G is cyclic. Does anyone have a guess? Well, it's true. Oh, wait, so from the previous question, from 4? So one of the things that you can prove, right, this is one of the consequences of Lagrange's theorem, is that any group whose order is prime is automatically cyclic. And in fact, the proof of that was basically you just choose some element, right? Like if the order of G is prime, fix some non-identity element, right? Let G be any element of G, which is not the identity. Then the order of G must divide the order of big G. Right? But big G is prime, so that implies that the order of G is the same as the order of the big group and therefore is actually cyclic, right? And in fact, it says that if you have a prime order group, not only is it cyclic, but every element that isn't the identity is actually a generator, right? So this is one of those little lemmas that was proven right after Lagrange. And if you forget it, it's okay. But yeah, that's just something to keep in mind. It's like this cool fact that if you have a prime order group, whether or not you even know a priori that it's abelian or whatever, it's automatically cyclic and therefore automatically abelian as well, right? It ends up kind of being one of these cool things. Yeah. Okay, so and the reason why I want to do 5 immediately after 4 is because 4 kind of gives us an idea of how to answer 5. So we have here that the order of G is 21, and this is a group. Now we probably don't have any ideas about groups of order 21 other than the cyclic group of order 21, right? We're trying to think like, is there an obvious non-abelian group of order 21? Maybe, maybe not. Nonetheless, this gives us a hint at the answer, right? We know that whatever G is, it is possible for every proper subgroup of G to be cyclic. Now, maybe every group of order 21 is cyclic. Maybe that's true. But on the other hand, maybe it's not. So the question is, can we find, I'm going to tell you right now, this statement is false. And the question is, can we find a counterexample? So can anyone think of a counterexample, right? This is a really bad spelling of cyclic. I'm going to fix this. Cyclic. And again, our counterexample is really motivated by question 4. Can we find something, a group, which we know is not cyclic, and yet its order is such that its only divisors are prime? Okay, so can anyone think of a non-prime order group, right? Here's our kind of idea. So if there's a counterexample, it's going to do this. So find a group G such that the order of G is not prime. G is not cyclic. But the only divisors of the order of G are prime. But the only divisors of the order of G are prime, right? Because then we'd be done. If we can find something like this, then we have our counterexample, right? Because every proper subgroup must divide, or every divisor of the order of G is prime. That would force every proper subgroup to be cyclic. And so if we can find something that satisfies this, we would have a counterexample. So just if we think about numbers, let's not worry about groups yet. Just if we think about numbers, what is the smallest number that you can think of, which is not prime, but is a product of, but whose only divisors are prime? Okay, so this is just a numbers question. The smallest number, smallest composite number, all of whose divisors are prime. 4. Does everyone agree? Right? 4 itself, certainly not prime. The only divisor, like the only proper divisor of 4 is 1 and 2, and you know, kind of ignoring 1. So that's 2. Okay, can anyone think of a group then of order 4 that is not cyclic? Does anyone remember it? We've seen one. Yeah, I'm trying to remember if U8 worked. I think U8 did end up being cyclic, but you're on the right track. So what was U8? So it was 1, 3, 5, 7, and 3. So we would get 3 to the 0 is 3, or sorry, is 1. 3 to the 1 is 3. 3 squared is 1. Okay, yeah. Maybe this one does work. Let's just double check. I had U12 in my mind. Okay, great. Yeah. So I had U12 in my mind, but yeah, this one I think will also work. 5 squared is 25. Yep. 7 squared is 49. Yep. Okay. Yeah, this one works. Yeah, like I said, I was going to do U12, but it actually, those groups are isomorphic. So perfect. Yeah, let's use this one. So U8 is not cyclic, right? And again, every single element in here, because it's not cyclic, that means that every element in here must have order 2, right? Or 1. So not cyclic, since every non-identity element has order 2. Voila. Okay, so here is a group that is itself not cyclic, but every proper subgroup of it is, right? Every proper subgroup of it is isomorphic to just Z2, but it is not Z4. Everyone agrees? That makes sense? So like that one, again, you can see like it's actually a relatively small answer, but you kind of have to think about it a little bit more, but exactly. All righty. Okay, so we've done like 2, 3, 4 now. I kind of want to jump back to question 1. So in question 1, you're told A and B are non-identity. That's important. Non-identity elements. Of different order. Okay, so they don't have the same order. This is important. The first time I did this question, I was like, I missed that part that they had to have different order. And I was like, wait a second, this isn't true. But yeah, so we're saying that they have to have different orders. And the order of G is 155. Obviously, that is an important number. Prove the only subgroup of G containing both A and B is G itself. The only subgroup containing, that's terrible, containing A and B is G. All right. So I think we should, take another little break, try and do this one. Just very quickly before we go, what are the divisors of 155? Let's do this together as a class. So the divisors of 155 are, okay, yeah, so yeah, 1, 5, 31, and 155, and that's it. Right? And again, something important happened. Look at these two numbers, right? Both, what's special about 5 and 31? Exactly, they're prime. So another one, this 155 is another one of these semi-prime numbers, right? It is a product of two prime numbers. So that's probably going to be really, really helpful. Let's take, again, 3 or 4 minutes and see if we can solve this one here using this fact, right? So big hint. Yeah, 5's prime. Why did I not say it's prime? Oh, maybe I did say 131. Well, it's on recording. We can go check it later. Yeah, 5 and 31 are prime. 1 is actually not prime, right? But 155 is a semi-prime. And semi-primes are actually really important. They do come up a lot in math. Semi-primes are numbers that are products of primes. So yeah, they do actually come up. But yeah, 5 and 31 are prime. That's going to be important. So give this a shot and see what you can get. Okay, so 3 or 4 minutes. We'll see where we stand then. And again, don't hesitate. Ask questions in the chat or come on mic, and I'm happy to answer things while we're waiting. Thank you. Yeah, thanks, Harvin. Okay, so let me say what I was saying again because I was speaking, but nobody could hear me. So what I'm going to do is basically just copy out Justin's argument. Justin nailed the nail on the head. So I'm basically just going to copy this out. So I'm going to suppose that A and B are elements of a group H, and I'm going to argue what could happen depending on the size of H, right? So if the order of H is 155, then H is the group, and I'm done, right? I'm finished. If H is either 5 or 31, both of these are prime, right? So then since A and B are both in H, that means that their order must divide H, but then that means that their order must be the order of H, right? Implies that the order of A is equal to the order of B is equal to the order of H because H is prime, right? So here I'm really using the fact that it's prime and these are non-identity elements, so their order can't be equal to 1. So their order has to be whatever the prime is, right? And this is a contradiction. Because we said, and remember what I said, that it was important that they had different orders. And I missed this the first time when I was doing this question before class. And I was like, no, this doesn't have to be true. But yeah, they're different orders. So this is kind of the important thing. And then finally, H can't be 1 because then in that case, it's the trivial group. And A and B in G, or in H, sorry. Well, again, it would even imply that they both have the same order, which would also be a contradiction. Order of A equals order of B equals 1, a contradiction, right? So we've shown that no matter what the order of H is, the only thing where this is possible is if the order of H is equal to 155, i.e. if the only subgroup that they were in was the original group, right? So we're done. Voila. Okay. All right, so that takes care of, what did we do? 1 through 5, I think we've now done everything of. So this one, again, I don't think this was hard. I do think it was tougher than some of the other ones that we did, which is why I kind of moved it and I moved the order around a bit. 6. Okay, so yeah, let's talk about maybe question 6 here next. So 6 asks you to do 2 things, but I did one of them in class, right? So on Tuesday, so it asks you to do the following. Let's not call this 6-1, let's call this 6A. So we did this one already, okay? So I'm not going to do this one again. Is G over K, right? So I proved this on Tuesday or Monday, proved on Monday. Okay, so what we're going to do is we're going to go straight to part B. And part B, this one is actually a lot of fun, but this one's actually quite tough. Like you definitely want to think about this. So again, what I want to do is give you a bit of a hint to bootstrap you into it. If you don't want a hint, just stop listening to me, right? Like take your headphones off, mute me, whatever you want to do. So if you don't want the hint, right, just ignore me. So for part B, we want to prove that G over ZG, remember Z is the center, right? It's the collection of elements which commute with everything. Cannot be prime. Right? And now here's our hint. Part A is our big hint. Basically, what I'd like to do, okay, so our hint is let's try and find another group. So let's find a group. Find a group H so that I can write G over Z of G as being G over H times H over Z of G. Okay, so in particular, this tells me that Z of G must be a subgroup of H, right? We just can't do this with anything. We need to have that Z of G is a subgroup of H so that I can write this. Now, if I can write this down, what we're going to do is we're going to assume for the sake of a contradiction that this thing here is prime, right? Excuse me. So if that's prime, what does that tell us about the right-hand side? Let's say it's a prime P. What does this tell us about the two numbers on the right? Right, one of them is a 1 and one of them is a P. What does it mean if one of these numbers is 1? All right, what does it mean if the index of a group over its subgroup is equal to 1? What could that mean? It means they're the same group, right? Because it means there's only one coset, right? So exactly. So let's say kind of note here, if G over H is equal to 1, if and only if H is equal to G, right? Because there's a single coset, right? That's what the index does, is it counts your number of cosets. If there's a single coset, that means that GH is equal to H for all G, but the only way that's true is if G is in H. So that gives you the inclusion that G is a subgroup of H, and the only way that's possible is if G and H are the exact same set, okay? So, I mean, if you want to formally prove that, you can. It's 1 or 2 lines. It's not a big deal, but as far as I'm concerned, for this question, you can assume it, okay? So let's think about what it is that we want to do here. If we can find a subgroup which contains the center, and we assume that G over Z of G is prime, then that subgroup must either be the entire group or the center of the group, right? And in general, this is actually true. There's nothing special about the center for which this is true. If the index is prime and I can find any other subgroup that contains it, then that subgroup must either be the entire group or the original subgroup. So what we want to do is we want to think about what are the subgroups of Z of G, or like what are the subgroups that contain Z of G, right? This is something that we learned earlier in the year. We learned there are these special things that we've played around with a couple of times before that contain the center of G as a subgroup of themselves. And maybe we can use that in order to construct a contradiction, okay? So this one's a really fun question. I want you to give it a try. Again, I'm going to give you about 4 or 5 minutes to see if you can think of what these might be. But I would suggest if you're having trouble figuring out where to start, go back and take a look at where we defined the center and look at the other things that we defined around where we define the center and see if that can give you a little bit of a hint of what you might want H to be. Okay, so let's try that. Again, I'm going to give you 5 minutes or so here, and let's see where we can get to. Okay, does anyone have a candidate? Something they, a candidate for H that they want to try, they think might work? Okay, interesting. So you want to take the centralizer of a subgroup. Which subgroup do you want to take then? Right, so you're saying you want to take CGH for some subgroup H? Okay, but what's H then? Like which subgroup of G do you want to take? Right, because in order to do this, you have to give me an H. So it's the right idea, but like which subgroup do you want to take? Maybe, but okay, well here, let's actually let's get rid of something first. So let's first of all say, yeah, G can't be abelian, right? So if G is abelian, then G over Z of G. What is G over Z of G if G is abelian? It's 1, and that's not prime, right? Is not prime. Okay. Is not, why can't I find my eraser? Is not prime. Okay, so let's assume now G is not abelian, just to make this more interesting, right? So suppose G is not abelian. Okay, so I guess, so you want to take any subgroup. I suppose you could do that. It just makes it a little bit harder to play around with, I think, if you take any subgroup, but I don't see any reason why not. The first thing you'd want to say is that there is a proper subgroup, right? You want to take a proper subgroup because the centralizer of G is probably not necessarily what you want to work with, because that would just give you the center, right? So you want to say like, this is, I have to take a proper subgroup, and then you have to argue that there are actually proper subgroups that exist, right? So you'd have to say, assume that G is a group and it has a proper subgroup H, and let's take its normalizer. And I think you could do that. I'm not 100% certain it'll work out. Did you manage to do that and get a full proof? Like, did your proof manage to work out that way? Okay, no, that's cool. So I think that's an interesting idea. Let me show you mine, and then you can tell me if yours is easier or not. Because if it's easier, I think it'd be really cool. So what I want to do is, because I know that G is not abelian, I'm just going to say choose some G, which is in G, but not in the center. Right? And we know that exists because the group is not abelian. And what I'm going to do is then, instead of taking the centralizer of an arbitrary normal subgroup, I'm going to take the centralizer of G, right? Right, because you don't have to take the centralizer of a group. You can actually take the centralizer of an element. Now that's the same thing as taking the centralizer of the cyclic subgroup generated by that element, but let's not worry about that. And so now, if I do my thing, right? By my thing, I mean, let's just write out what I had above. CGA Z of G, right? Or I guess, let me say, for the sake of contradiction, suppose G over ZG is prime, right? So let's say that this thing is equal to P. So what I'm going to do is I'm just going to break this into cases. So case 1, right? Well, like we said, one of these has to be prime. One of them has to be equal to 1. So let's say that G over CGA is equal to 1. Okay, so that means that G is CGA. Right? But that means that everything, or sorry, GGG, I'm using G, not A. Okay, so that means that everything commutes with little g, which means little g is in the center of G. A contradiction. Right? Case 2 is if I take the other thing, CGA over ZG to be 1, that means they're equal. But of course, I said that G was not in the center. But I've just now proven that it is in the center because it's certainly in its own centralizer. And that's also a contradiction, right? So it can't be prime. So can you tell us, Hung Wei, kind of like what you did? Was it similar? Right? Yeah, so I think what you probably did was similar. Was it about the same length, or was it longer, or was it shorter? Right, because I'd be sure, yeah. I mean, I guess in the sense that like I'd have to see exactly what you did, but it seems to me like it's going to end up being just a little bit more work. Like there's going to be a couple extra lines here and there because you've chosen a subgroup, a proper subgroup, which is not the center. And that's another thing too, right? Is you have to argue that your proper subgroup is not the center of the group. And then you're going to have to still want to play with elements in some way. But you're right. I think you can probably make it work. I think it's just going to end up being a couple of lines longer. And so it's totally fine if you want to work it out that way. But if you can type yours up and send it, even on Piazza or something, I'd love to see it because I'd like to see if it works. Because to me, it was just much easier to do the centralizer of an element rather than a group. But I think that's really interesting. I think that's cool. Okay. Now, everyone, really, really quickly, because class is over. So we didn't end up doing question 7. And question 7 says, show that, in a group of order 100, everything is either the power of a prime or has order 10, or there is an element of order 10. Very quickly, what are the divisors of 100? I think you all should be able to do this, right? Like this is not third-year university stuff. What are the divisors of 100? Oh, come on. Okay, Justin, yes, though I fundamentally disagree with the order that you wrote those down in, but yes, absolutely. So 4, 10, and then what? 25, 50, and 100. Did I get them all down? 1, 2, 4, 5. Oh, I missed 5, right? You're right. I should have trusted yours. 10, 20, 25, 50, and 100. Okay. So here are the powers of primes, right? And look at what's left over. Notice that the things left over are exactly multiples of 10. So it seems like if you should be able to argue that if an element of these orders exist, you can manipulate it to get an element of order 10. Does that make sense? Right? Like if the order of G is equal to 20, then the order of G squared is 10, right? So you can argue that, yeah, it's either 2, 4, 5, or 25. If it's anything else, then some power of it has order 10, which also satisfies what you want it to do. Does that make sense? And that's just like, I'm not going to write it all up because we're out of time, but that's how you would do it. Okay. Everyone's good? Any last minute questions?
Hold
Yeah.
on. Can I answer with the assignment?
Sure.
Okay. So for question number 1 on the assignment,
Mhm.
right? You had to show that x times y is equal to y times x squared, right? For
Sure.
that, we just had to assume the contradiction and then prove that it's not equal to the other elements inside of G.
Yeah, that's
So
how
it
I
can
do
only
it.
be equal to a yx squared, right? Okay.
Yeah.
So that's for that one. And then for question number 5,
Okay.
it said that prove that the set of positive rational numbers under multiplication is isomorphic to a proper subgroup of itself.
Yeah.
So for that, can I assume like B is a proper subgroup and then just show that using a map that the map is homomorphism and it's bijective, and then just assume that using the definition, just say that it's isomorphic? Or would I have to prove that the subgroup is a proper subgroup?
Yeah, you definitely want to prove it's a proper subgroup. Is D an arbitrary thing? Is it like abstract, or do you have like an actual concrete D that you're thinking of?
Oh, B. No, it's an abstract.
Yeah, I think you're going to want to do this by actually constructing the group, because I mean, if you just say, like, how would you do it? Because in fact, so this question is actually in the exercises in the book, right?
Mm-hmm.
And in the exercises in the book, there's a follow-up question to this, which is show that the additive rationals are not isomorphic to any proper subgroup, right?
Mm-hmm.
And you can imagine what I would ask then is, why does your proof not work in that case as well?
Right.
But I think that question in the exercises actually gives you a hint as to what the answer to this should be, like if you want to explicitly construct it.
Mm-hmm. Okay. Right. Okay. All right. I'll try it. All right. Thank you.
Okay. No problem.
So basically, I just have to prove that B is a proper subgroup, right?
I mean, there's going to be a particular one that you choose. And the hint in the book is a big one where you can just like prove very quickly that it is a proper subgroup, and the proof that it's isomorphic is very quick as well. Like there's a natural isomorphism.
Right. Okay. All right. Okay. Thank you.
No problem.
And how would I like? Can I get a hint on how I would do question number 2? Because that seems so like, I know that I could prove that G is cyclic, right? But how would I prove that the order of G is equal to P squared, where P is prime? Like that's where I'm stuck.
Okay, so choose a group has exactly one non-trivial. Right, so I'd pick an element that's not in the proper subgroup, right? And look at the subgroup generated by it.
Okay.
Right, and you know there's only one non-trivial proper subgroup, so it's either the trivial group, the proper subgroup, or the whole group. Right. And so now just look at those 3 cases, because I mean, one of them is trivial, right? The only way that element is the trivial, generates the trivial subgroup, is if it's the identity. Right. So now, just if you want to show the whole group is cyclic, you just need to show it's not the trivial subgroup, or the proper subgroup.
Right. Okay. All right. Okay. Thank you.
No problem. Hongwei, is it true that a group with order that's not a prime number must have a proper subgroup? Yes, but we don't have the theorem to do it. So there's something called Koshi's theorem, which says that if you are a prime, every prime divisor of the order of your group, for every prime divisor of the order of your group, there is an element in your group that has that order. Does that make sense, Hongwei? Like what I just said? So if I give you the order of a group and you give me a prime divisor of that order, then there is an element in the group that has that order in it. And so what you can see then is if you took the cyclic subgroup generated by that element, it would be a proper subgroup, right? So it is true, but we have not proved it, and we don't have the tools to prove that. In a week or 2, we will have the ability to prove the abelian version of that theorem, but not the general version. Does that make sense? Does that answer your question? Yeah, you can't use it. Yeah. And even the abelian version, like I said, in a couple of weeks, we'll be able to prove the abelian version, but the general version, we won't be able to, we will not prove in this class. We will not do the tools in order to be able to do it. But the theorem, if you want to look it up, which again, you're not allowed to use, but if you want to look it up just for fun, it's called Koshi's theorem. Okay, so Koshi's theorem is the result that you want. No problem. Okay, All right, everyone. So I think that's going to finish us off today. Thank you for coming. And I'll see you. Have a great weekend, and I'll see you all on Monday. Okay, thank you. Thank you. See you, everyone.